So Julie,
Thank you. Hello, everyone. So I'm doing my PhD at the CEA in France in collaboration with Mines Paris PSL. I'm going to present my work on the effect of heat treatment on fracture toughness and brittle fracture initiation mechanism of a quench and tempered nuclear pressure vessel steel A508 grade 3 steel. So first I will talk about the background of the steel, followed by a presentation of the material and its treatments and the testing condition. And finally, I will present my results and analyze them and conclude. So low alloy steels can be found in the primary circuits of pressurized water reactor nuclear plants, in particular in heavy forged components such as the reactor vessel, the pressurizer, and the steam generators. We study the fracture toughness of low alloy steel because the reactor vessel operating time determines the nuclear power plant operating time. Furthermore, the high thickness of these components induces wide variations of heat treatments from the skin to the mid-thickness, and it leads to a broad range of microstructures that have an impact on the mechanical properties. One of the main industrial challenges is to guarantee the integrity of the vessel, even in accidental cases. It is why we study the influence of quenching rate and the tempering condition on fracture toughness. For the material studied is an industrial A508 grade 3 forging from a ring shell from a hollow ingot of a steam generator. And coupons were extracted from a macroscopically homogeneous block. And this presentation deals with 11 different heat treatments encompassing typical heat treatment conditions observed on a heavy forging, with typical thickness is between 100 to 700 millimeters. We choose to study 4 quenching rates at 2 tempering duration at 640 degrees and 5 tempering condition at 2000 degrees per hour quenching rates. The study of impact toughness were presented at the previous edition of ECF and at Fontevraud 10 in 2022. And for the testing condition, for each heat treatment condition, we tested 12 CT 0.5T, with the geometry is represented on the right. We use the master curve method defined in the ASTM E1921. In this paper, the reference temperature, T0, is the temperature for which median toughness, KGC in 1T, is equal to 100 MPa square root meter. This method allows to pre-estimate this reference temperature based on Sharpie test by using the temperature for which the impact energy is equal to 41 joules. Based on this temperature, estimate temperature, we define 3 testing temperature, which are T0, plus and minus 25 degrees. Now, we will have a lot of master curves to compare. If we look at the effect of the quenching rate for the 2 tempering condition, we can note that we have better fracture toughness properties at higher quenching rates. And also we can note that the increase in T0 depends versus the quenching rate depends on tempering condition. We have 81 degrees versus 52 degrees. And this is 30 degrees beyond the 2. So this has a high impact of the quenching rate on the reference temperature. Now, if we look for a given quenching rate of 2000 degrees per hour, and we compare the tempering condition, we can note that the increase in T0 best tempering condition increased by 55 degrees for this quenching rate. And the important thing is that we have two sets of curves, one of low tempering parameter under 20, and a set of curve of high tempering parameter over 20. And we can note that we have a better fracture toughness for properties for tempering parameter under 20, around 90. Now we represent the reference temperature obtained during our experiments in function of the cooling rate in log scale. And we can note that for the two tempering conditions, we have a linear decrease in T0 with log scale of cooling rate from 800 to 8,000 degrees per hour. But this point is particular. We observe a drop of T0 increase at the quenching rate of 150 degrees per hour for the longer tempering time. One of the explanations of this drop is that the microstructure for the quench at 150 degrees per hour is the only one we still contain protected ferrite. And this quench is very slow. So it's more like a cooling that will quench. And there is a phenomenon of auto-tempering. And we can observe this may smooth the effect of the tempering after. Now, if we represent the reference temperature in function of the tempering parameter, we can, for each quenching rate, we can observe a plateau of T0 under 20, and then a rise of T0 after for a tempering parameter over 20. And this tempering parameter of 20 corresponds to a tempering temperature over 640 degrees or a tempering duration over 6 hours. And the two conditions can be combined. Another thing that the graph reveals is that we observe equivalence of fracture properties for a set of quench and tempering. For instance, for the 800 degrees per hour quenching rate, followed by tempering at 640 degrees for 6 hours, we have the same T0 that for the material quench at 8,000 degrees per hour, then followed by a tempering at 640 degrees for 20 hours. And this is quite the same for this point. Now, after all the testing fracture toughness tests, we realized factographic analysis of the broken specimen, and we were looking of the site initiation site, and we classify this in 3 types. First is the initiation on a carbide. Then I don't see if you see the blue at a grain boundary. The second type is inclusion, such often a cluster of inclusion, such as the titanium carbonitride in the big part, and then cluster with the magnesium sulfide here and here. And sometimes we can find rich oxide rich in aluminum and magnesium. And the third type is initiation at grain boundary, but with no visible particle. The carbides can be identified in a scanning electron microscope using a point dispersive energy spectrometry. And here is a typical spectrum of carbides in blue, which define the peak of higher enrichment of molybdenum compared to the matrix, and the higher peak of carbide, and less significant, but there is a higher peak of magnesium too. So we analyze 34 fracture toughness specimen broken around 100 MPa square root meter, and there is the frequency of initiation site types. So we have a predominant initiation on the carbide at grain boundary, then a quarter of initiation on inclusion, a quarter at grain boundary with no visible particle, and a few cases that we cannot define because the initiation sites were destroyed or not accessible. But if we look at this frequency of initiation types at a given quenching rate of 2000 degrees per hour, we order it by increase in order of T0. We can see that the evolution, the frequency of initiation on inclusion or on carbides evolves with T0, that we have an increase of initiation on carbides by increasing T0, and vice versa for inclusions. And now if we look at the same at frequency in order of T0, but at a tempering condition, we cannot that there is a plateau initiation on carbides for low T0, and then the frequency of initiation on inclusion increase by decreasing the temperature reference and by increasing the quenching rate. So to conclude, and for resume the presentation, on fracture toughness properties, we can note that there is a decrease in T0 with increasing the quenching rate, which was consistent with impact toughness. And also there is a rise of T0 for tempering parameter over 20. And about the Brittle fracture initiation types, we can note that globally carbide initiation types are predominant, but these predominant types depend on the tempering condition. Inclusion are more frequently observed at low tempering parameters and low T0, while carbides are more often observed at higher T0. Thank you for listening.